Yes. So this diagram, you can get more familiar with it. From this diagram, you can handle related question. All right. And no matter which way they ask you, you know this energy diagram. So this energy diagram, I put the formula on that first table. And this each transition can respond to one single line, either in absorption or the emission. See? For example, this one, this is called H alpha line, is actually the longest. Sorry, the shortest, the longest wavelength of Balmer transition, you can see between these two.
Yeah.
This will just remind you how to deal with this reflection and total reflection, can you see? We didn't have time to draw this diagram. When you are dealing with reflection, you should be able to draw the image in front of the mirror, flat mirror, you see? You remember how to draw the reflection in front of mirror?
Yeah.
Yes, good, okay.
It's same angle.
Yeah, you basically use a straight line, okay? You use a straight line. That's geometry. This is part of geometrical optics. These are the group of the polynomial diagram. Do you remember one question dealing with this one? They put several polynomial together, ask you the some property. Do you remember?
Yeah, so.
Yeah, so that will remind you. So that is the degree of the polynomial increase from straight line, from the constant to straight line to parabola, this kind of thing. That is another this is a diagram to illustrate how to find the torque. This is a seesaw, can you see?
Yeah.
So this central line, we always start in counting the distance of where you put in the force on. So this is called the rotation axis. Are you able to calculate this inclined motion with two objects? Do you know how to calculate work out the acceleration of this system, of this motion? Yeah, good. You need to build two equation, and by assuming the tension are the same, Can you see?
Yeah.
Okay. Another thing, I don't want to spend too much time, just in case, if you encounter the question ask you to find the force in the initial frame, like this one, you have to consider this so-called initial inertial force. Okay, that's perhaps this is the most challenging question I remember. Right. The idea is that in 90% chance we are dealing with inertial frame in which there's no acceleration other than the force caused acceleration, right? But if you imagine you are actually the rider of the bike, okay?
Yeah.
So you don't feel you are doing a circular motion. You're actually not moving. So in that case, you have added the so-called inertia force, which is opposite of the centripetal force. That's a little bit challenging. So that is why I think when we study the circular motion, sometimes you ask me, what is the centrifugal force, right? Centrifugal force is a good example of the inertia force, which we don't deal with if we choose the inertia frame. So, for example, when this green object could be the Earth, if they rotate about this center, we say that there is a centripetal force, okay, which keeps it turning the direction, okay. In that case, don't consider centrifugal force at all, right? The centrifugal force, which is opposite, which is away from the center, which is what you feel if you move with this object, okay?
Yes.
So some 99% chance you would not be asked this question, all right? Unless you are aware, for example, how can this bike be balanced? Without this force, can you see? This force is a centrifugal, can you see?
Yes.
Without this centrifugal force, how they cannot balanced. That is because we choosing the bike as a reference. Do you understand?
Right. Did you say that in non-inertial frame there is
Yep.
an acceleration or no acceleration?
Well, in the inertia frame reference, we have used a force to represent that acceleration, which is
Yes.
open, which just cancel. Simply use this force to cancel the acceleration. Does that make sense? If we just consider circular motion, right? Then we will know, if we just consider something is moving relative to you, then there's no centrifugal force because you are not moving with that moving object. Got it? Once you are not, if you are not in that moving circular motion object, then you will calculate the centripetal acceleration and centripetal force. Because we know that that object is constantly changing the direction of velocity. You agree?
Yes.
But however, once you are actually on the bike, if you can't see around, if you assume you cannot see around moving object, you will not feel you are moving. Just as we don't feel our moving on the Earth. Do you think so?
No.
The Earth is moving about the sun. Can we feel that? Can we feel where our Earth is moving about the sun?
So we are technically in a non-inertial frame.
Yes, that's right. That's right. It makes sense.
Yeah.
That's right. Anyway, this is ancient old story because that's why people refuse they consider Earth is the center of universe because they cannot feel Earth is moving.
Yeah.
Okay, understand? Well,
yeah,
just understand this idea. I think probably you will not encounter this question. Okay, this is the most challenging question. They also use a diode. You have to understand what can diode do. Okay, the diode you just follow the direction. They just allow the current go that direction. Can you see? This symbol of the diode indicates the direction of the current can go. For example, in this oscillating AC current, only these two up peak, which can go through this diode. So the output of this diode give you this just half, positive half of the AC current. Have you studied this in your ETA? No? Or just remember, this is just electronic. Diode is an electronic, this semiconductor device. Yeah. Which can only allow the current to go in one direction. That's all. Okay. In the DC current, we have no trouble because we know DC is always from positive to negative, right? Yeah. But in this, I noticed there in the past papers, they ask this question 2 times. All right. So this just know the diode is an electronic device. Okay. The current can go that direction along this arrow direction. Okay. The current cannot go backward. Okay. And also in just one occasion, they ask you the crystal structure, which is beyond the high school physics. Okay. But don't worry, you just treat it as an integer problem. All right. For example, H, K, L are integer. Can you see? These 2, 2, 2, 2, 2, 1, 1, 1 are just integers. Okay. You don't need to understand what that means. Oh, but it is related to this. Can you see? If you it's related to, do you know when we studied the plane, we use a directional normal unit vector.
Yeah.
ABC, that's 3 components. Okay. So these 3 numbers are related to that directional vector. Okay. So in other words, this number will represent a different plane. Can you see the gray colored plane? Can you see? For example, 100 will represent this plane, and 111 will represent this one. Can you see?
Yeah.
So don't worry too much. This is just like geometry, okay? If you have see this question problem, because you don't know, you have to study. So do you have any idea of the crystal structure or material? No?
Not really.
Okay.
Never studied that.
Well, if that's the case, you just follow the instruction to treat these three numbers. They will ask you the sum is equal to what? Okay, you just use their question. You don't need to understand.
Yeah, sometimes they give you the contents. Like
Yeah, that will give you content, but I just give you some information beforehand, so you will not surprised when you see this type of question. All right, you don't need to understand what this number represent. You just treat it as integers. Okay.
Yeah.
I think these are the useful diagram I will send to you, and these are formula. Can you see?
Yeah.
Let's show you how did I will explain to you how did I organize this table.
Okay.
So this got all formula I think is relevant. Okay, one is the force and the field. Can you see?
Yeah.
So I put all forces together. Can you see? Can you see? Can it's too small?
I can see.
You can see.
Yeah.
So first force is gravity. You see, which is always downward. Okay, but this formula is just for object near the surface. If you are dealing with a planet or the satellite, you have to use this general formula. You see.
Yeah.
Because after all, this G gravitational acceleration can be simply written as this formula. Can you see the formula here? Gravitational formula here. Now, I just put a different form force. So this is after I discuss Newton's gravitation law, which asks you many times, okay? So they should be, you'll be asked, I think it's very high. You were dealing with gravitational force, can you see? And mathematically speaking, this form is similar to the Coulomb force, okay? These forces they're all inversely proportional to r squared. Yeah. Okay. Then the Hooke's law, very important. You see, we're dealing with the spring. Do you remember? You can look at our older solution. Do you remember how to work out effective elastic constant?
What's effective?
So if you put several spring together, can you see?
Oh.
Yeah, sometimes you use two spring with different constant in series, sometimes in parallel. Do you remember that question?
Yeah.
Yep. So that is how you use. I will explain. We still have time. We can explain how to. I will just go back to that question afterward. Okay. So that is how this is a challenging question. Not just use Hooke's law, but they put several string together. You have to work out the effective elastic constant. Okay. Now this force, they ask this question once when we're dealing with oil drop. Can you see?
Yeah.
Small tiny oil drop. Basically, this force you see this dragon force, which is the proportion to the velocity. Can you see? If you drop the ball, can you see? If you, for example, the raindrop is falling from the sky, right? Each water drop will experience a dragon force, and which is also proportional to the size of this drop. Can you see that? Yeah. R is their radius. Imagine it is a sphere. Can you see? I forgot to turn on. This is also the air resistance force, which is like parachute. Okay, there's people jumping from airplane, the parachute, and the force will proportion to the velocity square. Okay, and this formula is used to determine to work out the terminal velocity. Do you remember the terminal velocity?
Yes. So
because
yes, we mean terminal.
The terminal velocity means that eventually they reach to the constant velocity.
Yeah, it's the V here equals to the terminal velocity.
The gravity equal to the air resistance force. That is from that equation, the velocity is called the terminal velocity.
Okay.
You can see if there's no air resistance, everything will free draw. It's called the free fall, right? However, because of the air resistance, the object will experience increasing resistance upward. This air resistance will be proportional to the velocity square. So eventually, when the velocity reaches a certain number, the dragon force will cancel the gravity when they equal to each other.
Okay.
Okay. This one is a fraction. Normally, this you have to know that this formula, but you don't have memorized. It's better to know there's such formula for the friction. Okay.
Yeah, I can memorize.
It's a coefficient multiplied normal force. And then we jump to the force in the formula of the field. Can you see? I put the force and the field together. If we know the electrical field, then the force acting on the charge will just equal to the product, you see, of the charge. Have you seen this formula before?
What's E here? Oh, is potential.
No, E is electrical field. I write down here.
But isn't B field strength?
Yeah, no, that's magnetic field. E is electrical field.
Okay.
Okay.
Yeah.
Makes sense? I
Yeah.
just put a few words here, just in case you. So this is the electrical field. Oh, sorry. Okay, so basically, if you put a charge in the electrical field, the force is just a product of the charge and E. Okay, and if you put the moving charge in the magnetic field, you have to use the right-hand rule, in which the force is always perpendicular to the field. That end up with a circular motion, right? And this is the formula for the field, the point charge field. They barely ask you this question, okay? But I just write down here for you. But they use this formula once. That is a field around the current carrying conductor. So you have to use the right hand to work out the field around it. You see?
Why is it over 2? It should be R. Wait, why is it?
This is the R. Sorry, this is R.
Yeah, that's
not
R.
T. Not T. Sorry.
Haha, spotted.
Yeah, that's good. You are very careful. Good. I think you'll be right. And in their formula, I remember they just simply ask. They just write this question, which is proportional to current. I think in one question they just use alpha to represent this constant, okay? I think you studied this formula in ETA, right? This formula.
Yeah. Okay. We're gonna test on it.
Okay. Now, most important thing is that why do we care the force so much? Because according to Newton, once we know the net force, then we can calculate that acceleration. So that is the idea of mechanics. Okay.
Yeah.
And of course, this form can be written as a change in the momentum as well. I just pick up this formula here, which is barely used. Okay, that's called the inertia force. Okay, but I hope they will not ask this question, but they do. If they did, then probably you will just think that we have added the inertial force to counteract, to balance that acceleration. This formula you know quite well. Can you see? These three, and these two are for the project motion. We used this before. If you choose that starting point, the launch side is at 0, if x, y. If you choose that origin, the launching side at origin, then you can use this simple formula to describe the project motion. Okay. And then we move to the circular motion. They always ask you circular motion. One formula is angular velocity is equal to the r multiplied v, right? Yeah. We use this a lot of time. And also the velocity can be divided equal to the circumference divided by the period, which also give you the formula for period. Can you see? Yeah. And the centripetal acceleration, of course, you know, if you write this is one form. Another form, if you use omega, if you use angular velocity, that centripetal force can be written as r multiplied omega squared. Omega is angular velocity. And in this context, I put the Kepler's third law here, because when we use Kepler's third law in high school, we assume that all planets are moving, are doing the circular motion, not ellipse. Okay, in general, it's ellipse. Okay. Oh, by the way, the force, the gravitational force is called the central force, because the force is only acting between the two mass center. In this force, the orbital can only get is the circle, ellipse, parabola, and what is a hyperbola. So these are the possible orbitals we can obtain mathematically. I remember you will see that one of the older questions, past paper ask you, they draw not of the circle, not of the ellipse, and not of orbit. Some are the circle, some are ellipse, some are parabola. So you have to select the wall. You have to select, but not a straight line. Okay. Another is the torque. So we mentioned the torque several times now. The torque is just extension of the force, right? The torque is, by definition, the torque is a product of the distance from the rotation center to the point where the force is acted. See? So the first formula is a cross product. The second one is just their amplitude. They also mentioned some called angular momentum. But this is something new for you, but don't worry. The angular momentum is just the cross product of the radius. Okay. And they also in one paper they use this so-called angular momentum conservation. But that if they ask this question, just follow their instruction. They will explain to you, all right? Yeah. So torque, basically torque, like force, is used to determine whether the object is rotating or not rotating. If the total torque is 0, there's no rotation.
Okay.
This torque is similar to the force, all right? Just remember that. And perhaps we'll also talk about energy formula. Can you see? These are all energy formula I can imagine. Can you see? So first is kinetic energy. Second is the potential energy near the surface. And the third one is the inelastic potential energy of a spring. And next one is the potential energy of gravity, which is more general. And also it can be written as integral. Why is the equal integral? I will explain, right? And this is a potential energy of the electrical potential energy. You see, and the next one is the photon energy. Photon energy have two forms. Okay, sometimes you have used lambda, sometimes you use the frequency. Sometimes they will ask you in the Einstein energy formula, energy and mass. So this gamma factor, you know the gamma factor in the special relativity, gamma factor. And one of the useful, these two energy conservation is very useful. This one represents the photon electric effect. I noticed that in the past, they asked the photon electrical effect twice. Okay. And this second formula is dealing with atomic absorption, where the energy is energy of hydrogen energy, hydrogen atom energy. Can you see the formula, right? So I put the RCH as a constant. And this N is integer.
Yeah.
Okay. This is what viral law we encountered there once. The idea, now I use our notation. I use EK for kinetic energy and EP for potential energy. Okay. So you don't have to memorize that. Just beware. If the potential energy can be written as the form, the R to the power of N, then there's a simple relation that this simple relation would exist. You see. Then we go to work and energy. So actually work energy it just give you example. Work and momentum. Sorry, work energy relation can be simply worked out from this Newton's second law. Can you see? If you multiply delta x on both sides, we can obtain this relation between work and the change in the kinetic energy. Similarly, I talk about the impulse. So I put the impulse law here.
Yeah.
So impulse law, if you what I'm trying to say is that you can derive this from Newton's second law. Okay. So work by definition, this is work formula, but this is a general formula. Sometimes if the force is changed, if the force is not constant, then you have to use this integral. For example, if you know the formula of the force, which is a function of R, then you can use integration to work out the work done. Okay. Yeah. Work done is equal to the change in the energy. That's a very important relation. And for example, when we start electricity, do you remember that work done is equal to the Q multiply the potential difference? Do you remember the formula in your ETA?
No.
Anyway, an important thing is the energy conservation law. There are two conservation law. One is energy conservation law. Another is momentum conservation law. So during the collision and explosion, right? Then we can use these two conservation law to build the two equations.
Yep.
And by the way, this is also the part of energy and work done. So when we start the photoelectric effect, the stopping voltage, can you see, is equal to the maximum kinetic energy of electron, right? In photoelectric effect. Now, these are other formulas. You know the formula, the circular motion torque. Yes, we have done that. Here, I also just mentioning that you ask, we discussed the difference between potential and potential energy. So that is why I put the potential formula in this category, but the potential energy in the energy category. Can you see? Potential is different from potential energy. The potential energy is equal to the mass multiplied the potential, if that is a gravitational potential. If it is electrical charge, electrical potential, then the potential energy, electrical potential energy, will equal to the charge multiplied this potential. So that is the difference between potential and potential energy. And in terms of the potential and the G, you have started calculus. The gravitational field strength G is equal to negative of first derivative of the potential. Okay, if you substitute this formula here, you will get this familiar formula for gravitational field strength. Do you know this formula? Yeah, this G. Can you see? That is how to derive this G. Can you see? I put the two formula because they are symmetrical. I put them together, easy for you to memorize. Can you see? Let's go to there. We talk about interference. So interference. So basically, they are dealing with two types of interference. One is a double slit. Okay. I think that they didn't actually. So they should ask this question. So I put the double slit formula here. The first formula gives you the constructive pattern, and the second gives you dark. Okay, this is destructive. Okay. And this is a small angle approximation, so you can work out how far the dark is or brighter position is from the central line. You see.
What is Y and L?
Y is the central line. So basically, Y. If I draw something here.
Y is the.
Yeah, one moment. I probably I put that. I will add that. One moment. Can I write down? Oh yes, I can write down. So So this I can include the graph for you. So if you have a double slit experiment, so this distance is called L, and this distance is called Y from the center. Can you see? That will form the angle. This is theta. So in this case, the theta, so tan theta is equal to Y over L. Can you follow me?
Yeah.
So this is screen. So this is screen. So the light comes from this direction. So we got these fringes here. Can you see?
Mm-hmm.
I will include this diagram for you.
Okay.
How can we get out from there? Oh, at the back. Okay, the bottom one. So these formulas they use several times. That is a condition to find the first dark ring. Okay, the dark. This is for the single slit or hole experiment.
Yeah. What
Okay.
does the n mean in the
n, n is n the integer. N from 0
the
to
number of
yeah, n is 0 from you put a number. Yeah, I put a number here. So
it's the number of dark band.
yeah, so n equal to 0. Sorry, from 0, 1.
Yeah, I'm just not sure it indicates dark band or bright band.
In this one, they only you only start one formula, which is for the first dark. This is first dark, okay?
Okay.
First dark. Because the central is bright, okay? They from this first dark, they can work out the how big the central bright spot is.
Yes.
They don't forget about, you don't need to know the general formula for the darkness for the single hole, all right?
What about double hole? What does n indicate for double hole?
Do you mean this n?
Yeah.
N is integer.
Yeah, the integer for what? The number of dark band?
I think if you want to know, I will tell you. So basically, these two patterns are different. You can see. If this, I just draw pattern, okay?
Okay.
For the double, this is center. For the double slit, and this peak is equal. Can you see?
Yeah.
They are symmetrical to each other. Can you see? So this is dark. Can you see? This n, there's n equal to 0 for the dark. And this n equal to this n equal to this is n equal to bright. Can you see this bright 2, bright 3? Can you see? So that's why how do you count it? This n equal to 1 for the dark.
Okay.
Okay. However, for the single hole, the pattern is looking like this. The central hole is bright, but the one getting very weak very quickly. Can you see?
Yeah.
So therefore, this formula is only for this first dark. So the first dark. That makes sense now?
Yes.
Because we don't care this much, because if you, this is a 2D, if you just see this pattern like this, you don't need to know the formula for this position, okay? You only need to know the formula for this first darkness, because that gives you the diameter of this bright spot. Can you see?
Yeah.
That the first dark ring give you the size of the central brightness. Okay.
Yeah.
With the question, we can slow down a little bit. How can we? Stop that. Go back. So that is interference, and continue the wave. So part of interference and the standing wave are all belong to wave. You see. So this of course, you know, this very most important formula between the velocity, frequency, and wavelength. This is for each end is fixed, and this is for one end is open, another is closed. And this formula has been mentioned in the ETA formula as well.
Yes.
Okay. And this is a Bohr model, so you can understand. You can Bohr model have different forms. So this is a Bohr model written in terms of wave, standing wave. You see, in this case, the wave is called the de Broglie wave, the matter wave. The wavelength is determined by the h divided by momentum. You remember?
Yeah.
When we started quantum.
Yeah, it's
and,
on it.
yeah. So that's why I put these two formula into the standing wave sectors. Can you see?
Yeah.
And if you do want to know hydrogen atom, this is original condition Bohr used. Can you see? This is original Bohr used, the condition Bohr used to derive his atomic theory. But if you combine this formula with the Bloch's wavelength, then Bohr's condition can be written as this form. If you have time, you can try.
Yeah.
And the Bohr model is important because that can be used to derive the energy formula. You see, this is energy formula for the hydrogen atom. I got plenty of space here. So from this energy formula, one moment. So from this energy, you know the n. So what is the range of n? Do you remember? What is 1?
From 1 to infinity.
Not equal to, yeah. So that just keep going. Okay. I'll put 3 here just. So you can use this formula together with that diagram I provided. See, energy diagram. Okay.
Yeah.
And Rydberg, the constant capital R is called Rydberg constant because Rydberg derived this formula before Bohr's theory. He can use this formula to describe the Balmer series, in which the first n is 2 and m is larger than 2. Do you know this formula? Are you familiar with this formula?
I know it, but I'll try to remember.
Yeah, exactly. Basically, when you see this part, when you see hydrogen atom, please refer to this energy diagram, okay?
Yeah.
That word you can see that is n equal to 2. For Balmer series, they come from n equal to 3 or 3 equal to 4. Any n larger than 2. That is a Balmer transition, you see?
Yeah.
So basically, in history, Rydberg found the formula, simple formula to explain this number, the wavelength, by using integer. So his mathematics is so superb, okay? But unfortunately, to pass this, I think sometimes they expect students to know more mathematics than just high school mathematics, just like how to play with integers, okay? But this is okay because it's still this is for the physics department entrance, right? Not for mathematical department entrance. So I think your algebra is okay. Okay, I just mentioned that in history they don't know the physics, but they can explain. They can work out the empirical formula to describe this wavelengths. This is very smart. Can you see these people?
Yeah.
They're very simple and very accurate. So that's why R is called Rydberg constant. But eventually, we understand the Rydberg constant can be explained by use energy formula proposed by Niels Bohr. This is just energy nuclear decay. So in which we have introduced a half-life time. You see?
Yeah.
Okay. And or just in passing, this is notation for the atom or the nuclei. You see? The mass number is the sum of 2 numbers, proton plus neutron. Can you see? And the atomic number or atomic order is determined by the number of the proton. You see, do you remember they ask you to count the mass of different isotope?
Mm-hmm.
So this is very similar to chemistry.
Mm-hmm.
But don't worry. Sometimes their question is extremely simple. Okay, but on the other hand, sometimes the question is extremely difficult. Oh, by the way, they have provided the two solution at the end of this past paper. Have you seen that?
Yeah, like to
one included 2019 one. They have provided two solutions, sample solution. At the end of this, if you have time, you can come have a look.
Okay.
But don't pay too much attention, especially I remember the last question we solved together. They have different. Maybe we didn't interpret their condition correctly, but I noticed the solution is very tedious, 2 pages. So forget about this question. So this question is sometimes extremely simple, but sometimes 1 or 2 questions can be extremely rare. Okay. So don't worry. I think you should be all right. I notice your personality is very good at this exam, because being nervous doesn't help. Okay, if you're getting nervous, you solve no problem. Okay, so just laugh at it. Okay, so just say, oh, I have bad luck. Okay, just remind you, bad luck. How could they ask such terribly difficult question? All right, just laugh at it. But if you can solve other basic question, easy question, your total mark will be very good. Okay, total mark very good. And I put this trigonometry formula here, just remind you. You don't have memorized, but I noticed that on several occasions they give you this formula. Okay, they know that, because this trigonometry formula is very useful when you're dealing with interference. That is the equation for the wave. Have you studied this form of wave equation? We didn't discuss this issue, because the wave, the sine wave, when the wave moving to one direction, can be written as 2 variables. One is the position, another is the time. And you know the omega. In eta we studied the omega t, this part, but this just all dealing with oscillation. If you want to study the moving wave, traveling wave, you have added the first term. The first term k is equal to pi over lambda, 2 pi over lambda. Have you studied this equation before?
No.
I just, well, it doesn't matter. So I just tell you, when we describe the wave is traveling, not a standing wave. Standing wave, the wave traveling in opposite direction, right?
Yeah.
But when you're dealing with a traveling wave, we have used this equation. When we put the 2 waves together, then we have to use a trigonometry formula. Do you understand? When you add the 2 wave up, then we have, because after all, you are dealing with the sum of like this function. Can you see? We use this formula before. We mentioned this formula before, right?
Yeah.
So don't worry. But I just read this trigonometry function here, just remind you, they might ask you this type of question. Okay, but what is this mathematically? They actually just found the sum of 2. For example, they say put the 2 waves together. What does that mean? They just found the sum of 2 sine functions. Okay.
Yes.
Last, we also put some mathematical formula for you, and this is of course this one. This is one. This is arithmetic. They are required. They didn't ask you arithmetic, but I put it here as well. Okay, it would be useful if they ask this type of question.
Yeah. Is there
conditional?
Yeah. Like
any other question?
Except the sum. I think there's another one, like finding the
The
Yeah.
common is another issue is found the common formula for each term, right?
Yeah, that
Yeah,
one.
that means you just by definition, you can use a definition, okay? But they ask you the geometrical sequence a lot, all right?
Okay.
Mm.
Also, the second one is arithmetic, right?
Yeah, second arithmetic, okay, and a conditional probability, yeah, you know how to use that. They ask this question several times, so be aware. Can you see?
Oh, I know that one. I know that one.
Yeah, they have to. They will ask the term what is the coefficient, right? And they ask it. And another useful is a polynomial. If they always give you some cubical equation, right? But they also assume they tell you there's one root. Okay, see, if giving a cubical equation, giving one root, then you can use this factorize. You can use non-division, right?
Yeah.
For example, if A is a root, then you can reduce this cubic from cubic to quadratic. Okay.
Yeah.
So once you got a quadratic, you can easily use the quadratic formula to solve the question. That is a formula I prepare based on the their scope of this test. All right. Oh, tomorrow! I didn't realize it tomorrow.
I'm gonna stock that in my brain.
It's okay. So you still have in the morning or in the afternoon?
Afternoon. I have
yeah.
special in the morning. So it's like
you have two exams. You have two exams.
Yeah. I'm so stressed.
Oh, it's okay. Okay. So I will send it to you. All right.
Okay.
I will send to you. So this is I hope you will pass this exam. Okay. Because I think you understand your math is good and you learn new things very quickly and don't be getting in panic. Okay, it's the pointless get panic. All right. It's,
I don't panic at all.
Yeah, because students get panic.
Yeah.
That's why it's bad luck. Okay, but you pick up the easy question first. Okay.
I think I'll just do this test for fun.
Just for fun. Another thing, psychologically, you feel
just I feel like I learned a lot from just studying the papers because I feel like the way of me thinking about mathematics and the logic thing has improved.
Very good point. You see, this test is emphasized analytical, right?
Yeah.
They need to derive the formula, found the dimension of formula, or the another thing here you have using the every quantity can be represented the second, meter, and the kilogram. You know this dimension. It's fun. It's just how could they use index node to deal with physics, right? So it's not of analytical algebraical skill you have to apply, all right? And so that is what I can provide this because I think it's good. I hope you will find some formula can be directly applied. Okay. Any question?
Not really.
You want to start some more about this how to use a particular formula? Let's just enlarge this one. Just enlarge this one. Do you want to ask me a question to use any formula which sounds unfamiliar?
Oh, I want to revise that spring one, the effective.
Which one?
I don't remember. It's the
Is a past exam
effective
paper?
elastic something.
What is the question?
About elastic, the springs, the effective energy or something. Effective force.
I can't follow which.
It's like the parallels and series of springs.
Oh, yes. Okay, one moment. I found that for you. One moment. Yes, yeah. I think you can also go back. I will pick up them. I think I saw it somewhere.
Is it energy or force?
I check your record. I keep the record for every student. I think one of them is level and spring. I think second. This one, this one. If this not one, will be the second one. Is there formula? This is a polycystin. Not this one. I just go to next one. Optic. I will check. All right. This is optics. You can also go through these solutions we did. Okay.
Yeah.
Or it's not. I saw it today somewhere. Paper. This is paper. Past paper. This one. Can you see? Can you see my screen?
No. It still stays on the formula sheet page.
That's interesting. Can we just stop here? I have to somehow could open. I stop this one. I'll probably try again to share the screen. Can you see my screen now?
Yes.
Can you see the question? The screen?
No, it stays on your file.
That's interesting.
Maybe it's because you opened another software and then they just stopped.
I just probably share screen. Can I share a screen? Can you see?
Yeah, I can see it now.
Good. So basically, they are looking for effective spring constant. Okay. And this is a challenge question for many students because nobody in Australia or nobody ask this question. Okay. But so basically, the idea is that you have to by definition, because you know the total force acting on this spring, 5 of them, right?
Mg.
Which is mg. And so what you need to know is to find the displacement, and knowing that the and each is in this case, this mg will divide by 2 spring. So the force on each spring, the lower one, lower 2 is half. Okay.
Yeah.
On the other hand, the mg is divided by 3 spring. So each force is 1/3 of mg. And based on this fact, then you can work out the how long the spring must be elongated, right? Extended.
Yes. So you let 1/3 f.
Where is our solution? Is this solution here? So basically, I remember we start from simple one. Can you see? From this simple one, we just consider this. I just my spring here. Okay. So can we start from this simple one? Can you see?
Yeah.
So we have 2 spring, which is identical. And if we want to find effective one, what do we do? We just knowing that the force at each point are exactly the same. Can you see? So in this way, we can find the tension. Can you see? And also the displacement is 2 delta x. Can you see? Or 2 delta x. So after we know this formula, then we can equalize this tension to this formula. So eventually we got something like this. Effective is half. You have followed this idea. Can you see? You can. So basically, we didn't solve this question directly. We started from a simpler case. Do you want me to explain? So basically, you have to determine the force acting on each spring. Okay.
Yes.
And which, of course, is always equal to mg, because this is a single string. You see, this is a single string here is mg. So based on this idea, and we will work out the force at each. So this is tension, because the total displacement will be delta x plus delta x.
Yeah.
Okay. So that is how. So basically, they use this idea. So the force. So if they have displacement, there's delta x, and this force, and that will determine this. So this force is proportional to the constant. So basically, that's why I write this formula that ultimately you have to treat this the force given is mg. So this part is mg, but the displacement, you have to be careful. The displacement is 2x now. So if you return, so the delta x is determined by the, each delta x is determined by the original constant k.
Yeah.
Okay, so that is applied to the, but the displacement change. The displacement is doubled in this case.
Yeah.
That is why the effective inertial constant is halved. So this, you can explain that. So this, if you put into in series, if you put the identical, if you put identical spring in series, identical K, then the effective will be halved.
Yes.
Can you see this? You're writing, right? But if you put in a parallel, can we start from 2? If you put the spring in parallel and the effective were doubled, there will be doubled. Can you see?
Yeah, because the displacement is still...
It's half. The displacement were halved because they don't need too much. They share the force. Can you see?
Yes.
If you just use this single, if you put the spring in series, everywhere the force is the same. All right.
I can get it now. Yeah.
Okay, I think you can go through our note here and you can see the recorded lesson. Okay, if you have trouble.
Yeah.
Okay. I think that is a part of the. I stop here. Okay. It's, well, have a look. Good luck. Good luck for your test. Okay.
Thank you. Thank you for organizing this.
It's okay. I will hopefully you can pass the exam.
Thank you.
Okay, I will send that a copy to you. All right, afterwards.
Yeah.
Goodbye.